We're going to take some notes on and talk about gears. So normally we would talk about this as a warm-up, but put these questions at the back of your mind as we talk here. What are some machines that use gears? Where have you seen them? What is the purpose of using gears? And what can they do that the wheel and axle can't? Why would we ever use them instead of our simple machine, the wheel and axle? So we want to know how are gears similar and different to simple machines. So in order to know that, you need to understand the word torque. Now, this is a very specific sciencey word that engineers and physicists use to mean a very specific thing. All it is really is just a twisty force. A force causes things to move. So if I push on this pencil, a force up and down moves in a straight line. But if I were to hold this steady and then push on it, well, then it becomes a torque because it's causing it to twist. They are very closely related and almost the same idea, but torque causes things to twist and torques cause things to twist and forces cause things to move. So we're going to talk about gears, pulleys, and sprockets. Gears are first up, but they all do the same thing. So this may sound familiar to what you learned in simple machines. So these things can change the speed of rotation, they can change the direction of rotation, and they can change the amount of torque available to do work. So this is pretty much the same thing simple machines did, except we're talking about torque now instead of force. And if you're thinking, you maybe are realizing that levers actually change torque instead of force because levers kind of rotate in a circle. So gears, anytime you have gears together, it's called a gear train. And that's when they mesh, right? The way gears meet is called a mesh. So that's just gears sticking together. They mesh together, they meet through these interlocking teeth. They will always turn in opposite directions. And if you want two gears to turn in the same direction, you need to add what's called an idler gear. Idle means doing nothing, right? So this idler gear doesn't change work or torque or anything. This would work the same comparing the first and the last gear if you had a small gear or a big gear here in the middle, but it just allows these two blue gears to spin in the same direction. Larger gears spin slower, so remember that. Unless they're locked on the same axle, then they have to spin at the same speed. So it's kind of like two people in the same car have to be spinning or have to be moving at the same speed. The yellow and blue gear are on the same axle, so they are spinning at the same speed, but the blue gear is bigger, so it's spinning more slowly than the red gear. You can see these little marks on the gear here that meet right now, those two black lines. The red gear has gone around once just now, and that blue gear has only gone halfway around. So even though it's one tooth per one tooth, that red gear will spin two times for every one time that blue gear spins. And the way we measure speed is revolutions per minute. How many times does it turn per minute? You may have heard of that and looking at car engines, things like that. So these are the variables that we use in our equations to explain gears and how they're working. So N is the number of teeth. D is diameter. And we don't really use that normally with gears. It looks like the letter W. It's actually omega. This is the Greek letter. You can call it W. Just W is used for other stuff in physics, so they added some Greek letters in. So that's just how fast it's spinning in RPMs. And this should actually be the Greek letter tau, which looks a little different than this, but it looks a lot like a lowercase t, and that represents torque. So there's tau. That's what torque is represented by. You can just draw lowercase t if you want. So yeah, these are the things. So if we look at these two gears spinning, these are how we would put numbers on it, right? N is number of teeth. There's no units for that. This red gear has 6. The blue one has 12. Diameter would just be the distance across. Like I said, we don't normally use that with gears. Omega, how many times per minute it's spinning. So this red gear could spin 40 times per minute, and this blue gear would be spinning 20 times per minute. And then the unit for torque is foot-pounds. That's another thing that's kind of confusing, and we will get more into that later. So how do you calculate gear ratio, right? Just like it's very close to mechanical advantage. So the number of teeth out over the number of teeth in is our gear ratio. the output diameter over the input diameter. Like I said, we don't really use that. Or careful here, this one is input speed over output speed. All right. And the torque out over the torque in. So notice all of these are usually out over in except for input speed. So if we look at our red and blue gear here, what's the gear ratio for this? Well, they should all be the same, right? It's all the same thing. It's gear ratio. So number of teeth out, this was 12, divided number of teeth in is 6. That gives us a gear ratio of 2. Diameter, 4 over 2, 2. All of these end up being 2. That is the gear ratio of these gear trains. So you can use any one of these pieces of data to find what the gear ratio is. And so what does that gear ratio of 2 mean? Well, if like the motor or input force is hooked up to this red gear, that gear ratio of 2 basically means that this blue gear has twice the torque. It is twice as strong. It's also twice as slow, or half the speed. So you're increasing torque, but you're decreasing speed with a gear ratio of 2. It's just like mechanical advantage. It's the same story we heard all last quarter. So just remember, bigger gears spin slower. So if we look at this picture here, let's say this red gear is the input. This would be connected to like a motor or an axle we're spinning. So sure, this green gear is slowed down, but it is much stronger. It would have a lot more torque. I'm not going to count the individual teeth on these, but I imagine this looks like it to be a gear ratio of probably about 4 or 5, maybe even 6. So this would be 6 times stronger. You could do that much more, create that much more torque to do hard work. Although the trade-off, as always, it would be going slower. So that is your lesson on gears. Thanks for listening, and we'll see you guys next time.